Hello, this is the screencast for Unit 5, which is on kinetics, and this one is for sections 1 through 4. And again, this slideshow is shared with you. It's in the Unit 5 review folder, so you could refer to that and click on those links if you want to watch some of those videos. And Unit 5 is typically 7 to 9% of your AP exam weighting. All right, so section 5.1 is on reaction rates. The learning objective here is explain the relationship between the rate of a chemical reaction and experimental parameters. So some of the essential knowledge, the first one, just an understanding of rates. A rate in general is anything per unit time. In chemistry, we usually talk about rates in change in concentration per time. So it's usually in units of molarity per second, or molarity could be moles per liter. So it could be moles per liter per second is usually what we refer to with rates. And some of the factors that affect rate, and we'll talk about this later when we talk about collision theory a little bit, but factors that affect the rate of a chemical reaction, those are listed over here. And basically what affects a rate is if you can get the reacting particles to collide more often and with more energy, they tend to go faster. They have a faster reaction rate. And you also want to know that rates of change and mole ratios. So looking at this reaction down here, if you know the rate of consumption of N2, you could say because the coefficient 3, it's a 3 to 1 ratio, you would say that the rate of consumption of hydrogen would be 3 times faster than the rate of consumption of nitrogen. And likewise, you could say the rate of production of NH3 would be twice as fast as the rate of consumption of N2. So you can use mole ratios to make comparisons between reactants and products. All right, 5.2, that section is on Introduction to Rate Law. The learning objective is represent experimental data with a consistent rate law expression. And the essential knowledge is you want to know the general format for rate laws. And this is a rate law down here, right there. So you have rate equals K, and then the concentration of each reactant raised to some power. And the power is the order of the reaction. So X and Y right here are the orders for A and B. And we can determine those orders a couple different ways. The first way, we'll look at the method of initial rates. And then you also have the rate constant. The rate constant is K. And once we know what X and Y are, we can take data from any trial and plug that in, and we can solve for the value of K. Okay, so the method of initial rates. When we do this, you look at different trials, and we try to figure out the order of each reactant. So to determine the order for A, we want to pick 2 trials where only A is changing. So we'd want to pick trial 1 and 3 because the concentration of B is staying at 0.20. So then you look and see, well, by what factor does A change? In this case, it doubles. So when the concentration of A doubles, and then you also look at how that affects the rate. You see by what factor does the rate change. So the rate goes from 0.4 to 0.8, so that also doubles. And now you can think of it this way. If we plug in the rate of change for each one of those, so it'd be 2 to the x power equals 2, so that x has to be 1. So that means x is going to be 1 for the concentration of A. So you say the order with respect to A is 1. Now we do the same thing for the concentration of B. You pick 2 trials where only B is changing, so you want to pick trial 1 and 2 because A is being held constant. and B is doubling, and the rate goes from 0.4 up to 1.6, so the rate is quadrupling. So to find the order for B, we would go the factor by which B is changing, so it's doubling, raised to some power y, equals the factor by which the rate is increasing, which is 4. So you say 2 to the y equals 4, so y has to be 2. So then once we get the rates, the order for each reactant, now we can rewrite the rate law. Rate equals K, A to the first order, and B to the second order. And that would be the rate law for this reaction right here. And then we could take, like I said before, data from any one of these 3 trials, plug that in to this equation, and we can solve for the value for the rate constant K. Okay, the next section is 5.3, concentration changes over time. The learning objective is identify the rate law expression of a chemical reaction using data that show how the concentration of reaction species change over time. And the essential knowledge here, this is basically just working with the integrated rate law equations. And these equations are all on your equation sheet. So you need to know there's 0 order, first order, and there's second order. So this is the 0 order rate law equation. And that corresponds with this graph right here. So 0 order, it's just concentration versus time will give you a straight line graph. And the slope of this, if you compare this equation to the line equation, the slope is going to be equal to negative K. So we can evaluate that. A first order equation, that's where natural log versus time gives you a straight line graph. So that's shown over here. Then in a second order equation, it's 1 over the concentration versus time. It gives you a straight line graph. And here the slope is positive K. So the questions that you'll see with concerning the integrated rate laws, you're not going to have to construct a graph. You're not going to have to calculate a slope. But you do want to know what graphs, you'll be asked to determine the order based on the graph. So you want to know what type of graph gives you a straight line for each order of equation. You also want to know, you won't have to calculate slope, but you want to know what the slope means. So like, for example here, the slope of a second order graph will give you the rate constant K. So that's the type of questions that you'll see with that. And also to go along with this, you want to know this half-life for first order. This equation is also on your equation sheet, and it's only for first order reactions. And the half-life is the amount of time it takes for half of the material to react. And you can relate the half-life to K using this equation right there. All right, and the last section for today is 5.4 on elementary reactions. The learning objective is represent an elementary reaction as a rate law expression using stoichiometry. And for the essential knowledge, first of all, know that elementary just means it's one step. So we can get the rate law from the mole ratios, or just by looking at the coefficients. What that means is if you have a one-step reaction, the coefficients for each reactant will be the order. So if we write out the rate law for this reaction, it would just be rate equals K, and NO to the second order because it has a coefficient 2, and oxygen to the first order because it has a coefficient of 1. And there you go, that's enough for today. Have a great day.